Okay, so today I'm going to give a talk called A Guided Tour of Sequent Formalisms for Modal Logics. And what I'll do first is just give a quick overview of what's going to be discussed in this talk. What I'm going to do initially is talk about proof formalisms, what they are, and then talk about something called the multi-sequent hierarchy, which is a way of organizing proof formalisms into a hierarchical structure, which gives information about how these formalisms relate to each other. Now, rather than talking about classes of sequent calculi for classes of modal logics, which I think can be a bit confusing, what I'm going to do is use a single running example and talk about how different proof systems relate to each other by means of this example. Now, the example that I've chosen is called Gödel-Löb provability logic, or GL for short. And I've chosen this logic for a couple of reasons. First of all, it has deep connections to Gödel's incompleteness theorems and the provability predicate of piano arithmetic, which is quite interesting. Second, it's quite easy to characterize. You can take the modal logic K and just extend it with a single axiom. And third, and most importantly for this talk, is that GL admits a large number of different style of sequence systems. So GL, for instance, has labeled sequence systems, nested sequence systems, linear nested systems, Gentzen systems, and also non-well-founded and cyclic systems, which makes it a very good case study for understanding how these different formalisms relate to one another. In this talk, I'll be primarily focused with the labeled, nested, linear nested, and Gentzen formalism for GL. I'll talk about how we can translate proofs between them, and I'll talk about the trade-offs that occur when we transition between formalisms. Okay, so since this is a talk on proof formalisms, I thought we ought to define what a proof formalism is. I've given a definition on this slide. A proof formalism is a paradigm for constructing proof calculi, characterized by a shared data structure and style of inference rules, giving rise to a family resemblance among the systems that it generates. Now, that's a bit of a mouthful, but the two defining characteristics of a proof formalism are highlighted in bold. The first aspect is that of data structure. So what are the data structures used in proofs? And by data structure, I mean one of two things. Either the choice of sequence that you're using. Are you using trees or lists or regular old Gentzen sequence? Depending on this choice, you're either going to have syntactic cut elimination. It's going to have an effect on how big or small your proofs are. It's going to also have an effect on how counter models are extracted from failed proof search. This choice is critical when defining a proof formalism. The second aspect of data structure is the structure of the proofs themselves. So typically in proof theory, proofs have a well-founded tree structure, but they don't need to have this shape. They can be graphs, they can be infinitely big, they can be non-well-founded. Today I'm going to be focusing primarily on proof formalisms that have the standard structure of well-founded trees. The second defining characteristic of a proof formalism is the style of inference rules used. So for instance, labeled sequence systems for modal logics tend to encode frame conditions directly as structural rules, which manipulate the structure of labeled sequence. By contrast, in nested sequence, we tend to use what are called propagation rules, which propagate logical data throughout paths inside of a nested sequence. And those paths are defined relative to frame conditions for the logic. As a third example, display calculi make use of so-called residuation rules to display certain parts of a sequent. And that allows you to apply logical rules to this little part of the display sequent. And having this control over where logical rules are applied allows for one to prove syntactic cut elimination quite easily. So these two aspects are the defining characteristics of a proof formalism, and you might think of a proof formalism essentially as a way in which you design calculi. Now in this talk, I'm going to primarily be focusing on the data structure aspect. So this relates to this next slide. On this slide, I've written what I call the multi-sequent hierarchy. And if you're not familiar with what the term multi-sequent means, it essentially means a generalization of a Gentzen sequent, so a more complex data structure in which Gentzen sequents are embedded. And what I'm going to do first is talk about what's written on this slide, and then afterwards I'll explain the significance of it. So at the base level of the multi-sequent hierarchy, we have Gentzen sequents, which are essentially the atoms from the standpoint of this hierarchy. Going one level above, we have so-called hypersequents, which are multi-sets of Gentzen sequents. And we can see that when this multi-set is a singleton, it subsumes the class of Gentzen sequents. This is essentially true of everything in this hierarchy. Each class of sequence higher up in the hierarchy captures the class of sequence lower on the hierarchy. Above hypersequence, we have linear nested sequence. These were introduced in 2015 by Gödel-Löb, and they are a refinement of Andrea Massini's two-sequence introduced in the 1990s. And these are ordered lists of Gentzen sequence. Note that when the order does not matter, this reduces to a hypersequent. So you can think of a hypersequent essentially as a commutative linear nested sequence. Above linear nested sequence, we have nested sequence. These were introduced independently by Robert Bohl in the early 90s and Ryo Kashima in the late 80s. And these are just trees of Gentzen sequence. Above this, we have labeled sequence, which were originally defined by taking the Kripke semantics of a logic and integrating it into the syntax. So we think of, for example, the labels like X, Y, and Z as representing worlds in a Kripke model. We think of the relational atoms as representing the accessibility relation. But from a syntactic perspective, labeled sequence are nothing but graph sequence. So this multi-sequent hierarchy is a product of a project that I worked on during my PhD, where we studied translations between different kinds of proof systems and proof formalisms. And the idea was to take this jungle of formalisms and see if we could coherently organize it. We found that we could effectively organize proof systems on the basis of the sequence that they use, or multi-sequence. Now, there are a few facts about this multi-sequent hierarchy which are perhaps a bit evident once you have this hierarchy in place. So for instance, we found that translating proofs up the hierarchy tends to be quite easy. So if I take a proof in a hypersequence system, it's quite easy to embed it into the labeled sequent proof because I'm embedding a simpler structure into a more complex structure, whereas translating proofs down the hierarchy tends to be quite difficult. And this has to do with the fact that you have to remove structure when you translate proofs down the hierarchy, and it's not clear how to always do this in a soundness-preserving fashion. Second thing is that as we move up the hierarchy, we tend to be able to capture more and more modal logics, so bigger and bigger classes, in a cut-free and analytic fashion, which makes sense intuitively because we have more structure, so we can define more proofs for these logics, and therefore more cut-free proofs. A third fact is that if you take a theorem, the set of its proofs that it admits within one of these formalisms tends to grow as you go up the hierarchy as well. Again, that has to do with the fact that there's more structure when you have richer multi-sequence that you're using, so it admits more proofs. Now today I'm going to focus on the labeled, nested or tree, linear nested in line, and Gentzen formalisms for the modal logic GL. And what I'm going to do is try to answer the following questions. The first one being, how do we translate proofs between these formalisms? I'm going to show how to do that. I'm going to talk about what the trade-offs are as you transition between formalisms in terms of proof complexity and computational complexity relative to proof search. And I'm going to also talk about what properties are gained or lost, like invertibility, how spaces of proofs expand or contract as you transition between formalisms, and also how the choice of formalism affects proof search. So one thing that we find is that systems which typically have optimal complexity tend to not support counter-model extraction, at least in the case of GL and similar p-space logics. Okay, so in this next section, what I'm going to do is talk about Gödel-Löb provability logic. I'm going to explain how this logic came about historically, so you have a bit of an understanding of how to read the modalities. I'll talk about the semantics for this logic, and I'll also talk about its axiom system. I think this will be helpful for understanding how to read the sequence systems that I'll discuss later on. So GL has its roots in the work of Kurt Gödel. Right? Gödel in 1931 famously proved the incompleteness theorems, which are shown on this slide. I'm going to assume that everyone is familiar with this, and I'm not going to go into that much detail about it, but the crux of Gödel's proof, right, establishes that there exists a sentence G, which we call the Gödel sentence, which is equivalent to its own unprovability, that's what this stands for, in Peano arithmetic. So it effectively says, I am not provable in Peano arithmetic, with PR being the provability predicate of PA. Now, around 20 years later, Leon Hankin comes around and decides to ask a question about this provability predicate. He says, we know that Gödel's sentence asserting its own unprovability is unprovable. What can be said about the sentence asserting its own provability? What can we say about a sentence S which is equivalent to its own provability in Peano arithmetic? Well, around 3 years later, Martin Löb came around and gave an answer to this question. And he showed that if the provability of A implies A in Peano arithmetic, then it must be the case that PA already proves A. Now, at first sight, some might think this is a bit trivial, but it's not. This is a non-trivial result, and it does give you some ways to recognize true but unprovable formulae underneath the assumption of consistency of PA. So here is Löb's theorem. It's shown formally in the middle of the slide, and the way that Löb established this theorem is by using certain properties of the provability predicate, which are enumerated on the bottom of the slide. The first property says that A is provable. If A is provable in PA, then one can show in PA that, or one can prove in PA that A is provable. The second property says that in PA, one can prove that if A is provable and A implies B is provable, then B is provable. And the third property shows that in PA, one can prove that if A is provable, then it's provable that A is provable. Now, for those who are familiar with modal logics, you'll notice a certain similarity here. If we replace the provability predicate with boxes, then the first property is just the necessitation rule, the second property is the K axiom, and the third property is the transitivity or for axiom in modal logic. And we refer to Löb's axiom, or we learn this Löb's theorem, shown here as this formula, as Löb's axiom in modal logic. Now, this was what came out of this work, is that folks realized that you could reason about the properties of the provability predicate of PA by making use of a simple modal logic. So that's how the provability logic came about through this long historical process. And the language for GL is just a typical modal language. You have propositional atoms, falsum, implication, and you also have the box operator. This is a classical logic. You can take the remaining operators as defined, like negation, disjunction, conjunction, and the biconditional. I've chosen this signature, by the way, because it minimizes the number of rules in the sequence systems that we will look at. In GL, we interpret formulae over special kinds of Kripke models. So these are triples. I've given an example Kripke model here to demonstrate the properties that these models have. So the first component of the model, W, consists of a set of worlds. This can be finite or infinite. The relation R is a binary relation over the set of worlds, which is transitive. We all know what that means. And also conversely well-founded. So this is not a first-order definable property, which is what gives GL its unique fixed point flavor. What this property effectively says is that if I follow any sequence of edges inside of my model, this process eventually terminates, which means that I cannot have any cycles, for example, inside of my model. We can see that R satisfies this property here in this example model, right? Because if we look at any sequence of edges, they all eventually terminate. So it's encoding that converse well-founded property. V is the valuation function, which, as usual, maps propositional atoms to worlds, meaning that proposition is true there. So we think of GL as being, one way to characterize it semantically is to think of it as the set of all validities over these models. Truth conditions are as usual, right? P is true to world if the valuation function deems it so. We have that falsum never holds. A implies B holds at a world if A holds there, meaning that if A holds there, then B holds there. And we have that box A holds at a world W if and only if for all points in the future of W, A holds. And we can axiomatize GL by using the axiom system shown here in the middle of the slide. We just take an axiom system for classical propositional logic, extend it with the K axiom, the necessitation rule, that's the modal logic K, and then add Löb's axiom to this axiomatization. Note that sometimes people include the for or transitivity axiom. It is in fact a theorem of this axiomatization, so you could include it as an axiom if you wanted to, but strictly speaking, it's not necessary. And it was already shown that this axiom system is sound and complete relative to the Kripke models that I mentioned earlier. So you can think of GL either as K, extended with Löb's axiom, or the logic over transitive, converse, well-founded Kripke models. Okay, so what I'm going to do now is talk about the different sequence systems for GL and how they relate to each other, and what the trade-offs are as we transition between formalisms. I'm going to initially begin by talking about the most complex system and work my way towards the most simple system. The reason being is that translating proofs from complex systems to less complex systems is the interesting and difficult translation. So we'll start with labeled, And then I'll introduce tree sequence and talk about how to go between these formalisms. Then I'll talk about how to go from tree to line sequence, and then from line sequence to Gentzen sequence. And all these transformations are p-time. So this will show that all of these systems, despite having very different proofs, structured proofs and very different sequence, do p-time simulate one another. Okay, let's talk about labeled sequence first. A labeled sequent is an expression of the form G, gamma, turnstile, delta, where G is effectively a set of what are called relational atoms, which are objects of this form, X, R, Y. So in labeled sequence, we have an infinite set of labels at our disposal, X, Y, Z, U, V, and we can think of these essentially as representing vertices in a graph. And what G does is it captures the edges that are occurring inside of that graph. So it's telling you how these vertices relate to each other, or the edge relation is given by R. Gamma and delta are taken to be sets of labeled formulae. A labeled formula is just a formula where a formula of GL where you've prefixed it with one of these labels, X. And we can think of a labeled sequent as encoding a binary graph of Gentzen sequence. I've given an example to demonstrate this concept on the bottom of the slide. So here's an example of a labeled sequent, and this is the graph that it encodes. So let's see how you go from the labeled sequent to the graph. You can think of the labels, as I said before, as vertices inside of this graph, X, Y, and Z being the vertices. The relational atoms, as I said before, encode the edges inside of the graph. And then the labeled formulae tell you which Gentzen sequence are labeling which vertices of the graph. So I have A associated with X in the antecedent. So this means that I have A turnstile empty set being associated with X. I have C and D associated with Y in the consequent. So I have empty set turnstile CD associated with Y. I have B associated with Z in the antecedent and E associated with Z in the consequent. So that gives me the Gentzen sequent B turnstile E associated with Z. So that's all really a labeled sequent is. It's just a graph of Gentzen sequence. Now, two labeled sequence systems, which are sound and complete for GL, were given in a 2005 paper. And I've written one of these systems here on this slide. So it has 3 axiom rules or nullary rules. So these can be used to begin proofs. I'm going to talk about the ID and the false and left rule first. Effectively, what the ID rule is saying is that if I have a graph of Gentzen sequence, and there's some vertex, called it X, where the Gentzen sequent at that vertex X has both a P on the left-hand side and a P on the right-hand side of the Gentzen sequent, then that counts as an axiom in this system. The false and left rule says something similar, but where you have a graph of Gentzen sequence, and at least one of those Gentzen sequence has falsum occurring in the antecedent. We have the implication rules. The way that you read rules, by the way, in this system, I tend to read them bottom up. So a rule is sound if and only if the invalidity of the conclusion implies the invalidity of one of the premises. So if a labeled sequent is invalid, what that essentially means is that I can interpret all of the labels as worlds inside of some Kripke model. And I have all of the accessibility relations defined by the graph G holding. And I have that all of the labeled formulae in the antecedent are true based on how labels are interpreted as worlds, and all of the labeled formulae in delta are interpreted as false. So that's what it means for a labeled sequent to be invalid. So in the implication left rule, if I wanted to explain why it's sound, I would need to show that invalidity of the conclusion implies invalidity of one of the premises. So if the conclusion is invalid, that means that there is some world, X, where I have A implies B being true, which means that either at X, B is true, or A is false. So at least one of these is going to hold. For the implication right rule, I would have that at X, A implies B is false, so at whatever world X is interpreted as, which means that at X, A is true and B is false. Okay, so that explains why these rules are sound. For the box left rule, the reason why it is sound is because if the conclusion is invalid, then there's some model which makes everything on the left-hand side true and everything on the right-hand side false. So that means that in that model, I have X seeing Y, I have box A being true at X, and therefore A would be true at that future point Y, according to the semantics. In the box right rule, I have that at some world x, box A is false, which means that there's a point y in the future of x where A is false. And also, in this box right rule, I add this formula here called the diagonal formula, which is essentially a copy of the principal formula that gets copied into the antecedent. Now, what this does is this effectively encodes the converse well-founded condition from GL into this proof system. Okay, so that's how that frame condition is being encoded, by making use of this diagonal formula. This makes cut elimination quite difficult for the system. It can still be done, but that's how that second order condition gets encoded. And the last two rules of the labeled sequent calculus are called structural rules. So the irreflexivity rule is capturing the fact that inside of our models we cannot have cycles or loops. And the transitivity rule is saying that bottom up, right, reading this rule bottom up, if I have x relating to y and y relating to z, then I know that x relates to z according to the transitivity rule. Now I want to note one thing. The irreflexivity rule is technically not needed for completeness relative to the logic GL. The reason why is that if you take a proof that ends with sequent arrow xa, so just some formula, some theorem at some particular x, if I apply rules from this calculus bottom up, you'll notice that something happens. Inside of the implication rules, the graph structure is always preserved bottom up. In the box left rule, that's also true. The box right rule introduces a fresh label y, so it introduces a new edge inside of a graph. And the TR rule introduces transitive edges. So this means that if I have a proof that ends with essentially a tree consisting of a single vertex and a Gentzen sequent of the form turnstile A, then thinking of the proof in a bottom-up fashion, all of the labeled sequents that occur are going to be transitively closed trees. Now, it's never the case that cycles can occur in transitively closed trees. So that means that this irreflexivity rule will never occur in such a proof. Therefore, this rule is not strictly needed for completeness, and one can do without it. That's going to be important later on. Okay, to show how the system works, I've given an example of a proof on this slide. As usual, in proof theory and with sequence systems, we oftentimes typically construct proofs in a bottom-up manner. So here is a labeled sequent proof of Löb's axiom. And taking Löb's axiom at x, if I apply the implication right rule bottom up, it decomposes this implication connective, putting the antecedent into the antecedent of the sequent and keeping the consequent in the consequent. The box right rule takes this box formula on the right-hand side and unpacks it. So I introduce a fresh label y that x sees, where I have p occurring at y in the consequent, and I have this diagonal formula getting introduced into the antecedent of the premise. Applying the box left rule bottom up allows me to take xry and take this box formula and unpack its contents at y. And then if I apply the implication left rule here, it introduces a box p on the right-hand side here and a yp on the left-hand side here. I can see that this is an instance of ID because I have the same atom occurring on the left and the right. And I haven't shown it here, but I have the same formula occurring on the left and the right here. I can apply the box right and the box left rule bottom up here to finish the proof construction process. I just haven't included it here because the slide, this proof would not fit on the slide if I had that. But this proof can be finished via a couple rule applications. Okay, that's an example of a labeled proof. Let's now look at tree or nested sequence systems for GL. So a tree sequent is effectively a restriction of a labeled sequent. It's an expression of the form T gamma turnstile delta, which encodes a tree of Gentzen sequence. T is a collection of relational atoms, just like G was before. It's a set of relational atoms, which encodes a directed tree. And these tree sequences have to satisfy two conditions. The first is that if T is non-empty, so if it contains some relational atoms, meaning there's some edges in the tree, it has to be the case that the labels of the labeled formulae occurring in gamma and delta have to be a subset of the labels in T. This ensures that the tree is connected. So it is indeed a tree. The third condition says that if T is empty, so there are no edges in the tree, then this is just a tree that consists of a single vertex. So that means that gamma and delta, all the labels that of the labeled formulae that they have are at most one. There's only a single label labeling these formulae. And so this encodes essentially just a single vertex with some Gentzen sequent that is labeling that vertex. So as I said before, a tree sequent is a tree of Gentzen sequence. And I'm given an example here of a tree sequent, and you can see the tree of Gentzen sequence that it encodes on the right-hand side. As before, we have that the labels represent the vertices in the tree, the relational atoms are corresponding to the edges in the tree, and then the labeled formulae are determining the Gentzen sequence that are associated with the various vertices. Okay? Note that there are no labeled formulae associated with Z, therefore the empty sequent is associated with Z. Okay, before I move on to discuss the tree sequent calculus for GL, I just want to make I want to make a quick mention about equivalent formalisms that appear in the literature. So the notion of tree sequence was given in a 2007 Tableau paper, this restriction of labeled sequence that I just mentioned, but there are equivalent formalisms that have been introduced as well. So, which are essentially all notational variants of one another. So tree hypersequence were introduced by Gödel-Löb in 2009, and nested sequence were introduced originally by Boll and Kashima, as I mentioned earlier, and further work was done in 2009 as well by Kai Brunner. So what I've done here is I've shown I've given three examples. This is an example of a tree sequent. This is an example of a tree hypersequent where the parent-child relation is given by this slash, and the sibling relation is given by this semicolon. And here's an example of a nested sequent. And all three of these different strings, you might say, or different representations, all three of these things are different representations of the same tree of Gentzen sequence shown on the right. Now, throughout this talk, I'm going to use the terminology here synonymously, but I'm going to try to stick to using the tree sequent terminology. But these are effectively all the same thing. Okay? They all encode trees of Gentzen sequence, just using a different notation. Okay, so Gödel-Löb gave a tree hypersequence system for GL, technically gave two systems in a 2009 paper, and here is that system in the tree sequent notation. So this calculus is very similar to the labeled sequent calculus we saw previously. We have the ID and the falsum left rule, which I discussed before. We have the implication rules. We have the box left rule. We also have the box right rule. Now, this calculus really differs from the labeled sequent calculus in two respects. The first is that it uses tree sequence as opposed to labeled sequence, which is why we have T's here instead of G's. And the second is that it does not make use of structural rules. It doesn't make use of irreflexivity or transitivity. And it couldn't make use of these rules because in these rules, bottom up, what these rules do, or at least what the transitivity rule does, is it introduces a non-directed cycle into the structure of a sequent. And since we're working with trees, we can't have such structures. So the way that transitivity gets encoded is a bit different. It gets encoded by means of what's called a propagation rule, given by this for left rule. So how does this rule encode transitivity? Well, let's read it bottom up in the way that I mentioned earlier. If we have x relating to y, and we have that a holds at all points in the future of x, which is what box A means, then since our models are transitive, it must be the case that a also holds at all points in the future of y. So this rule is encoding the transitivity property, but just doing it in a different way. So this system is really just the labeled sequence system minus the two structural rules of irreflexivity and transitivity, using this for left rule instead, and restricting to a tree-like structure. Okay, what I'm going to do now is talk about the correspondence between these two systems, the labeled one and the tree sequent one. And I'm going to explain this correspondence in a high-level fashion. So I'm not going to go into the nitty-gritty details. I'll talk about the other proof transformations between the different formalisms in more detail for the sake of time. But I'll just explain the two main mechanisms that are used here. So the correspondence between these two proof systems can be seen as a consequence of the theorem shown on the top of the slide. This is recently published work with Peter Ostropolsky-Nalovaya, who is a professor over in Wrocław, who's actually published last month in Transactions on Computational Logic, despite having been online for a few years. And in this paper, we showed that every labeled sequent calculus satisfying a certain set of conditions, effectively it has to be characterized by certain kinds of Horn conditions, can be transformed into a p-time equivalent tree or nested sequent calculus and vice versa. And the way that we show this theorem is essentially as follows. We show that every labeled sequent calculus and tree sequent calculus can be thought of as a type of algebra that operates over colored graphs or colored trees, and that each of these algebras or calculi can be transformed into a lattice of p-time equivalent algebras or calculi. And we recognize in this paper that the bottom elements of lattices effectively can be thought of as labeled sequence systems, and the top elements of lattices can be thought of as nested or tree sequent calculi. And so we say that nested sequence and labeled sequence are dual to one another because they inhabit these opposite positions on these lattices. And we show that by eliminating structural rules from these labeled systems, we can translate proofs up the lattice through various different points until it becomes a tree sequent proof. And by reintroducing structural rules, we can translate proofs down this lattice until it becomes a labeled sequent proof. Now, the nice thing about this theorem is these conditions are quite general. So they encompass a large number of proof systems for a large number of different logics, including propositional logics, first-order logics, classical logics, intuitionistic logics, multimodal logics, and of course, various provability logics, GL falling underneath this umbrella term. And also, this general result gives us also some general proof complexity bounds. So we find that proofs tend to grow at most quadratically as you transition from the tree sequence setting to the labeled sequence setting, and they tend to shrink by the same amount when you go backwards. So what this means is that if you have dual tree and labeled sequence systems for a particular modal logic of interest, and you want to define a proof search algorithm using one of these systems, from the standpoint of worst case complexity, it's not really going to matter which one you use, because most of the modal logics we have that we have these kinds of systems for are NP complexity or above, and these p times simulate each other, with their proofs only being differentiated by a quadratic amount. Now we can take this idea of structural rule elimination and introduction and use it in the setting of GL. So recall that the tree sequent calculus is the same as the labeled sequent calculus without the structural rules, plus this propagation rule for left and restricted to tree sequence. And I've written these rules here so that you can reference them. Earlier I mentioned that the irreflexivity rule is admissible. It's not needed for completeness in the labeled sequent calculus, and you can essentially show that any labeled sequent proof ending with a tree sequent does not need instances of the irreflexivity rule, so you can just ignore it. And we can use the idea that I mentioned on the previous slide to provide proof translations between these different systems. So given a labeled sequent proof of a tree sequent, what we can do is we can identify transitivity applications, the TR rule applications, and we can permute them upwards in the proof. And they either get removed at the axioms or they get absorbed into the box left rule. And when this happens, this can introduce for left rule applications. And this will, through TR elimination, will give you a tree sequent proof as the output. And you can also do the opposite, reintroducing TR applications and removing for left applications to go from the tree sequence setting to the labeled sequence setting. Note that a similar result was given by Rajiv Gore and Ravanta Ramaniaka in 2012, but they showed a correspondence between a different labeled and a different tree sequence system for GL, and that correspondence is a bit more involved because these systems do not have as nice of properties. They have slightly different proof theoretic properties than G3KGL and CSGL star. But it predates this theorem and is still quite similar, but a bit more involved. Okay, what I'm going to talk about now is the relationship between the tree sequence system and the line sequence system for GL. So let's talk about what line sequents are. A line sequent is just a restriction of a tree sequent to using lines. So that's what this L stands for. Gamma and delta as before, are sets of labeled formulae, but now L, instead of being a tree T, is just a line of labels. So a line sequent can be thought of as a line of Gentzen sequence. Line sequents are notational variants of linear nested sequence, again given by Lellman in 2015, and the fact that these are notational variants was also observed by Björn Lellman and Eleni Pimentel in a separate paper. So here's a line sequent. This is the type of ordered list or line that it encodes of Gentzen sequence. You can see that the relational atoms correspond to these edges, and the labeled formulae give rise to the Gentzen sequence that are tagging or labeling the various vertices here. And we can rewrite this in the original linear nested sequent notation as shown here, where this double slash is separating the elements of this list. Okay, so a line sequence system for GL was given in 2005 in a CSL paper that I published, and this system is really just the tree sequence system for GL restricted to using linear structures. So it is almost the same with only that one difference. But this difference does make does have an impact on the proof sizes, as I'll explain over the course of the next few slides. So we have the same kind of axioms, we have the same implication rules, we have the same box left rule, the same for left rule encoding transitivity, and the same box right rule. Note that when this rule is being applied bottom up, X is essentially the vertex of the last component of the line sequent, and when Y gets introduced, you're extending that line by a new element and adding effectively a Gentzen sequent that has box A in the antecedent and A in the consequent. But the proofs here are defined in the same way. We're just using linear structures as opposed to trees. Okay, so let's talk about how we can translate from the tree sequent formalism into the line sequent formalism in the context of GL. This process is a two-step process. So what we have to do first is take our tree sequent proof and put it into something called end-active form. And after it's in this end-active form, we can then, in a top-down fashion, prune trees or provide what's called a linearization procedure to extract a line sequent proof. So this is a two-step process. I'm going to explain the first step right now. So what is an end-active tree sequent proof? At a high level, an end-active tree sequent proof is a tree sequent proof where all of the action is happening at the leaves of the tree. Okay, so when you read the proof bottom up, all of the auxiliary formulae are going to occur at leaves of the tree. So what does that mean in particular? That means that in instance of ID or falsum left, the principal formulae, their labels are leaves inside of the tree sequent. The second condition says that the principal label of an implication left or implication right rule is a leaf. And condition 3 says that the principal and auxiliary labels of a propagation rule like box left or for left are pre-leafs and leafs respectively. What I mean by pre-leaf, by the way, is a parent of a leaf node. And the fourth condition says that box R is just always considered to be end active. Bottom up, this introduces a fresh point, which is a leaf inside of the tree. We just consider it to be end active. To demonstrate this concept, I've given an example of an end active tree sequent proof, which also doubles as an example of an end active line sequent proof. And I'll explain why each of these inferences are end active according to this definition. So at the base level, we have effectively a single vertex in our tree, X, and we have the for axiom or transitivity axiom stored there. And when we apply the implication right rule bottom up, we're just affecting this leaf vertex X. Box right is always considered to be end active. It extends with X or extends the structure by adding a new fresh vertex that X points to, which looks like this. And now when I apply the for left rule bottom up, I shift box P from the pre-leaf X to the leaf Y. So you can see that the action is happening at the very end of the tree, at the leaf node. This box right application is also end active, trivially by the definition. It introduces a fresh point Z, which Y sees. And now the box left rule application unpacks this box P at Y and introduces a P at Z, Again, the action is happening at the leaf node. And finally, what happens is that we have P associated with Z in the antecedent and the consequent. The ID rule fires, this ends the proof, and again, these principal formulae are occurring at the leaf node. Okay, so that's an example of an end-active proof. Now, what one can show is that if you take a rule from the tree sequent calculus, ignoring the box R rule because it's always end-active by the definition, if R is a non-end-active instance of the rule, and R prime occurs underneath it and is end-active, then you are free to permute R below R prime. So I've given a couple examples here on the slide. I'm not going to go into too much detail about them, but on the left-hand side, we have a non-end-active application of implication right, followed by an end-active application of box right. Then we have a non-end-active application of box left, followed by an end-active application of for left. And as shown on the right-hand side, you can permute these two to derive the same bottom sequent from the same top sequent. Okay? So using this lemma, we can prove the following theorem. We can show that each tree sequent proof of a theorem, so sequent arrow XA, can be made end-active. Now, since the proof ends with a sequent of this form, the last inference has to be an end-active inference. Okay? There's no other way to derive such a sequent. You have to have an end-active inference. And what that means is that the proof of sequent arrow XA has a bottom end-active fragment. What you do is you look at the bottommost non-end-active rule application and you permute it downwards into the end-active fragment using this lemma until it becomes end-active. Since trees, the tree-like structure of these tree sequence has to shrink as we go towards the conclusion, because the conclusion ends with a tree that's a single vertex with a single formula associated with it. This means that eventually, when you permute these non-end-active rule applications downwards, they're going to have to become end-active. Right? Eventually, the principal labels are going to have to be leaves or pre-leaves, respectively. Okay? So this theorem can be shown by just doing rule permutations using this lemma. All right, and now let's talk about the next step. So what I've explained so far is that every proof in the tree sequent calculus can be put into end-active form. What I'm going to do now is show how we can take such a proof and we can prune trees to recover a line sequent proof. And to do that, I need to explain this pruning function, which is going to be defined on this slide. So let bold T be a tree sequent, and I'm going to have B be a branch, which is just a list of labels or vertices, and such that x1 sees xn through some sequence of relational atoms. And what the LNS function does, this stands for linear nested sequent, by the way, so paying homage to Lellman's work. What the LNS function does is it takes as input a branch B, so a sequence of such labels, and it takes as input a tree sequent, bold T, and it outputs the line sequent that is associated with those labels. So it retains the line of relational atoms shown here and keeps only those labeled formulae which use the labels from x1 to xn, so inside of that branch. And each of these is defined here, by the way. Okay. So to show how this works, here's an example of a tree sequent. This is shown as the graph on the right-hand side. B is a branch, X, Y, W. And we can see that when I plug the branch and bold T into the LNS function, it gives me this line sequent, which corresponds to this red line, this branch of this tree sequent. Okay? So we're going to use this function in the following theorem. What we're going to show is that every end-active proof of a theorem in the tree sequent calculus can be transformed in polynomial time into an end-active proof of the same theorem in the line sequent calculus. Okay? And I'm going to take you through the various cases of this proof. So we're going to show the following. If we have a proof of a tree sequent, an end-active proof of a tree sequent bold T in the tree sequent calculus, then there exists a branch B in that tree sequent such that if I plug the branch B in the tree sequent T into the LNS function, it has a proof in the line sequent calculus. And I'm going to show this by induction on the height of the tree sequent proof. Okay? So in the base case, we assume that the height of our tree sequent proof is 1. So it's an instance of ID or falsum left. I'm going to show the ID case. So suppose we have a tree sequent proof of height 1, an application of ID. And what I need to do is find a branch B such that if I plug this tree sequent with B into the LNS function, the result is a provable line sequent. Well, it's not hard to see what branch you ought to choose. We're going to let B be the branch in T that starts at the root and ends at X, where these two principal formulae, XP, occur. If I do that, my line sequent has the following shape. And I have that these two copies of XP, one in the antecedent, one in the consequent. This is an instance of ID, so this line sequent is provable as well in my line sequent calculus. All right? That's the base case. The falsum left case is done in pretty much the same way. All right, let's look at the inductive step now. I'm going to show the implication left and the box right cases. The other cases are similar, if not simpler than these. These really are the interesting cases. So let's consider the implication left case first. I'm going to suppose that my tree sequent proof ends with an application of the implication left rule. T1 represents the left premise, T2 represents the right premise, and T represents the conclusion. Now, by the induction hypothesis, I know that I have two branches, B and B prime, such that if I plug B and T1 into the LNS function, I have a proof in the line sequent calculus. And if I plug B prime and T2 into the LNS function, it also has a proof in the line sequent calculus. Now, there are two different cases to consider here. The first is that X is a vertex along both branches, or 2, that is not the case. I'm going to show both cases, but we'll show one first. Now, in the first case, because X is a vertex along both branches, because this rule application is end active, that means that B is a branch that starts at the root and ends at X, and so is B prime. Since this is a tree, that means that both of these branches have to be identical to each other. All right? So that means that if I apply the LNS function with B to T1, it returns a line sequent. And in particular, because it ends at X, I have this XB occurring in the antecedent. If I apply the LNS function with B to T2, then I have this line sequent as the output, where I have this XA occurring. Well, the nice thing is that both of these line sequents are of the required form to be able to apply the implication left rule. So if I apply the implication left rule, I get the following, which is the translation of the conclusion with the branch B. Okay? So the case goes, the inductive step goes through in this case. Okay, let's consider case 2. Suppose that either B or B prime does not terminate at X. Right? I'm going to suppose without loss of generality that B is the one that does not terminate at X. Well, in this case, what happens is, if we look at this inference rule, all of the action is happening at X. Right? That's where the only change is taking place. The rest of the tree sequence that are appearing in this rule application are completely unchanged if we ignore X. So that means that I can take the translation of the conclusion to be equal to the translation of the left premise. And so that pushes this case through. All right, let's look at the box R case now. This one is also quite interesting. So I'm going to suppose that my tree sequent proof ends with an application of box right. T prime is the premise, T is the conclusion. And by the induction hypothesis, I know there exists a branch B, such that if I plug B and T prime into the LNS function, I have a proof in the line sequent calculus. And there are 3 cases to consider here. Either my branch B goes through X and Y, or it goes through X, but then it goes in a different direction and does not go through Y, or it does not go through X and Y. Right? That's the third case. We'll consider each case in turn. Each is resolved in a different way. So in the first case, we suppose that the branch B goes through X and Y. So if I translate the premise as shown here, then I get the following line sequence. Notice that I have XRY occurring, I have Y box A occurring and YA occurring, and this is the required data that I need to be able to apply the box right rule. So if I do that, I obtain the following line sequence, which is the translation of the conclusion with B, the branch B without Y. Okay, so that pushes this case through. In the second case, I assume that B goes through X but not Y. So what happens here, if I take the LNS function of the premise with B, it gives me some line sequence. And if I were to take the LNS function with B in the conclusion, it would give me this line sequence. The only difference between these two is that there is an X box A occurring in the consequent here. And I didn't mention this earlier, but the weakening rule is admissible in the line sequent calculus, so I can just apply the weakening rule here to weaken in the box A. Okay? And that pushes this case through. In the third case, we have that B does not go through X or Y. This is quite similar to the second case that we looked at in the implication left case of the inductive step. Here we have that the translation of the conclusion is identical to the translation of the premise. Since the branch does not go through X or Y, there's no change that happens whatsoever along this line sequence that is occurring within these tree sequence. Right? So that's the end of this proof. The other cases, as I said before, are done in a very similar fashion and tend to be quite easy to argue. Okay, here's an example of applying this algorithm. On the top of the slide is a tree sequent proof, and on the bottom of the slide is its corresponding line sequent proof that you would obtain by applying this linearization or pruning procedure. I'm not going to go into that much detail about what's happening here, but I just want to explain what's happening at a high level. So in the tree sequent proof, because branching is allowed, what can happen is we have all of this data occurring in other branches, and we can even perform inferences on it, okay, which are not strictly speaking needed to be able to establish the conclusion. What this theorem that I just described tells us is that this orange data is really enough to be able to establish the conclusion, and instead of performing any inferences on this blue data, I could just weaken it in when it is needed. So this is one of the reasons why proofs are smaller in the line sequence setting as compared to the tree sequence setting, not only because we're using simpler structures, but also because we do not have these redundant or unnecessary inferences happening on tree sequence that are not really core to the proof, okay? And I've given a visual to try to explain the relationship between the space of proofs of these two systems on this slide. So trivially, it's the case that every line sequent proof is a tree sequent proof, and effectively what my theorem has done is it's shown that I can, after doing this end active step and putting a form and every proof into an end active form, I can translate all of my proofs into this bottom gray fragment. So this bottom gray fragment is sound and complete for GL. And if you analyze proofs between the tree sequent calculus proper and the line sequent fragment, you'll notice that if you look at branches of proofs inside of the tree sequent calculus, that these tree-like structures can be exponential in the size of the conclusion. So proof branches are exponential in the tree sequence setting, whereas in the line sequence setting, branches of proofs will be polynomial in the size of the conclusion. So this has ramifications for proof search in these two different systems. What this means is that if we write a typical depth-first proof search algorithm in the tree sequence setting, it's going to be exponential space, while if we write a typical depth-first proof search algorithm for the line sequence calculus, it's going to be p-space. And by depth-first, what I mean is that you're essentially constructing branches of the derivation at a time, trying to see if a proof exists, okay, as opposed to constructing the whole proof, which would have a higher complexity. All right, let's talk next about the relationship between the line sequent calculus and the Gentzen sequent calculus. So a Gentzen sequent calculus was given by Salmon and Valentini in 1980, and it's quite simple. It's shown here on this slide. It only consists of 5 rules. So we have an ID and a false and left rule, kind of like before. We have the implication rules, sort of like before. We're not using any graphical structure now, though, or any labels. And we have the so-called box GL rule. Now, in the previous systems that we saw, labeled, tree sequent, and line sequence setting, we had separate rules for the box operator that introduced it on the left and the right-hand side. And we also had rules that encoded transitivity of the box operator, right? Either by means of the for-left propagation rule or the transitivity rule in the labeled sequent calculus. The box GL rule is encoding all of this information simultaneously in one inference step. So when we translate from the line sequence setting into the Gentzen sequence setting, we will have to take chunks which are called blocks, of modal rules from the line sequent proof and translate them as a single box-GL application. So I'm going to talk about this rule, box-GL, which is doing the heavy lifting for the modal reasoning in the system, because it encodes a lot of information simultaneously. So you'll notice, first of all, that sigma and delta are not copied bottom up. This is effectively encoding the weakening rule into this system. The box A rule is unpacked bottom up. This is encoding the semantics of the box operator. And at the same time, we have the diagonal formula, which again is encoding converse well-foundedness. We have that box gamma is copied bottom up. This is encoding transitivity, and also we have that we strip gamma of its boxes as well, shown here, which is encoding the semantics of the box operator. So pretty much all of these different semantic conditions are encoded in this one rule here. Okay, so how do we translate from the line sequence setting into the Gentzen sequence setting? So this process is essentially a two-step process. What we have to do first is we have to put the line sequent proof in something that I call normal form. And what that means is that reading the proof bottom up in the line sequence setting is going to consist of repetitions of blocks of rules. Okay, so what I call a complete block is a structure of the form shown here on this slide. A complete block starts reading bottom up with a box right rule application, followed by some block B of 4 left rules. What a block of rules is, by the way, it's just a sequence of 0 or more applications of those rules, right? Some finite sequence of these rules. That's all that a block is. So B is just some number 0 or more of 4 left applications. And this block B is preceded by a block B prime of 4 left rules, which is preceded by a block B double prime of implication left and implication right rules. And then the top of this complete block can be either instances of ID or falsum left, or they can be further applications. They can have further applications of box right above them, which means that we then have the same structure repeating higher up. Now I'm going to refer to this part of a complete block as a modal block. And that should make sense because this part of the block has the box right rule, the 4 left rules, and the box left rules associated with it. Right? So this is doing the modal reasoning. And these entire modal blocks are going to be translated essentially as single box GL inferences. That's the significance of them. Okay? So note that every line sequent proof can be transformed into an end active proof in normal form that satisfies these conditions. Okay? So let's now show how to go from the line sequence setting to the Gentzen sequence setting. We're going to show that every end active normal form proof of a theorem in the line sequent calculus can be transformed in p time into a proof of the same theorem in the Gentzen sequent calculus. So let pi be an end active normal form proof of xa in the line sequent calculus. We're going to translate the proof pi in a bottom up manner. Okay? So that means that we're going to start with the theorem xa, which then just becomes the Gentzen sequent turnstile A in the Gentzen calculus. And now the idea is to make a case distinction on the other rules that are applied bottom up in pi, and we're going to take the end components of a line sequent. The end component of a line sequent is the Gentzen sequent that is stored at the very last vertex. And we're going to translate those into the Gentzen proof to reconstruct a proof in the Gentzen sequence setting. Now I'm going to show 2 cases here. The implication left and the box right cases, and note that the implication right case is similar. So if I'm translating my proof bottom up, the proof pi from the line sequence setting into the Gentzen sequence setting, if I encounter an implication left rule, then I will have already, by the induction hypothesis, have its end component occurring in the Gentzen sequent proof that is being constructed. And I can translate this inference by just translating the end components of both premises as shown here. And you can see that that corresponds to doing an implication left inference in the Gentzen proof bottom up. The implication right case is effectively the same. Let's now look at the interesting case. Okay, if we're translating pi bottom up, we might eventually hit a box right application. Well, now since our proof in the line sequence setting is in normal form, this means that this box R application is preceded by a modal block. So that means that I have some application of box R where I have this principal formula and the auxiliary formula shown in orange, which is preceded by some number of applications of for left. So it's taking some box formulae and shifting them to the leaf node Y, or the terminal point Y that was introduced by the box right inference here. And this block of for left inferences is preceded by a block of box left inferences where I'm unpacking these box formulae at Y as well. Now note that the box sigma 1 formulae are those which are principal in the for left inferences only. The box sigma 2 formulae are those which are principal in both of these blocks, and the box sigma 3 formulae are those which are principal only in the box left block. And I've made this little distinction here because it makes it a bit easier to see how we obtain the how we translate this into the Gentzen proof in the output. So we'll notice something here. We have a line sequent at the bottom of this modal block, and what we do is we have by the induction hypothesis that the end component of this line sequent already occurs inside of the output Gentzen proof, and I notice that the end component of the premise of this modal block, shown in orange here, can be obtained in the Gentzen setting by bottom-up applying GL followed by weakening. Right? This data here is effectively the same as the data here. And by just continuing this process in the line sequent calculus, I can effectively construct a Gentzen sequent proof as the output. Right? So that's how this theorem works. Here's an example of that theorem. So on the top slide, I have a line sequent proof of Löb's axiom. I'm using B here as a macro that is equal to box P implies P. The reason why is that if I didn't have this B occurring here, then the proof would be too big and it wouldn't fit on this slide. And I'll show you how this translation works in this concrete setting. So again, I translate my proof in a bottom-up fashion here. So I take the conclusion and I just make that the conclusion of the Gentzen proof. I apply implication right, which gives me this sequent. I translate that as shown here in blue. And now this section of the proof here is a modal block. So I've hit a modal block during this translation procedure. I can translate this modal block by having an application of box GL followed bottom up by an application of weakening. And this data shown in orange is the end sequent of this line, right? The Gentzen sequence stored at the terminal vertex of this line. Continuing this translation, I apply implication left on B, which is an implication formula. In my right premise, this gives rise to this line sequent, and the end component or end sequent can be translated as shown here as an instance of ID. In my left premise, I now have another modal block that I've encountered. And I can translate this data by just applying the box GL rule bottom up, and that gives me an instance of ID. So note that this weakening rule is not always needed in the translation, but sometimes it is. Okay, so that shows how this algorithm works. So here's a slide comparing these two different systems, sort of showing what we have learned by means of this translation and just comparing them based on what happens in their proofs. So in the line sequence setting, one can show that given a proof of a theorem, that line sequence are essentially quadratic, most quadratic in the size of the conclusion, while trivially in the Gentzen setting they are linear. We can give a p-space procedure in the Gentzen sequence setting. This has been done a long time ago. And we can also, this is new work, which a master's student and I have just submitted for publication. We can also show that you can do a p-space algorithm in the line sequence setting. We do have that all of the rules are invertible in the line sequence setting, but not in the Gentzen sequence case. You might say that the line sequence calculus has more modularity because you have separate left and right rules for the box operator and a single rule that encodes transitivity. while everything is just encoded in a single rule here. And one thing that is interesting is that the proof search algorithms in both of these systems, despite being complexity optimal, because p-space is the complexity of GL, neither of them support counter-model extraction. You have to extract counter-models from entire derivations in both cases. So you can get a p-space algorithm, but if you do that, you lose counter-model extraction. And your algorithm essentially requires non-determinism or backtracking to stay within this complexity class in proof search. Okay, some final remarks about what I've discussed. So the full picture of everything I've discussed is shown on the top of this slide. As I mentioned earlier, we can eliminate structural rules from the labeled setting to go to the tree setting and reintroduce them to go in the opposite direction. We can use this linearization or pruning procedure to go from tree sequent proofs to line sequent proofs. Line sequent proofs are trivially tree sequent proofs, so going in the opposite direction is trivial. Using normal forms, we can extract Gentzen proofs from line sequent proofs, and we can use a translation from Lellman 2015, which effectively reverses this transformation that I gave. So in this paper, this transformation from line sequent proofs to, or from linear nested sequent proofs to, from Gentzen to line sequent proofs is not shown for GL. It's shown for other logics, but it can be applied here. And I haven't shown this transformation, but it's very easy to show how to embed Gentzen proofs into labeled sequent proofs. And this occurs, a description of this occurs in my 2025 CSL paper. Okay, so what we find is that all these systems simulate each other in polynomial time. So that means that using one formalism versus another is not really about power, but it's about convenience. What properties do you want your proof system to have? What application are you using these proof systems for, right? This is the question you have to ask yourself. And here is a table that explains the various differences and compares these different systems with one another. So given a proof of a theorem in the labeled sequent or tree sequence setting, sequence can be exponentially big in that proof in the size of the conclusion, while in the line sequence setting, it can be polynomial or it's linear in the Gentzen sequence setting. We have invertibility in all of the multi-sequence systems, but not in the Gentzen system of rules. I would argue that we have high modularity in the labeled and tree sequence systems, and only, say, a medium amount in the line sequence system and a low amount in the Gentzen system. What I mean by modularity is the ability to modify the system so that it becomes a sounding complete system for a related logic. This is typically done in the labeled setting by removing or adding structural rules, and it's done in the tree sequence setting by modifying propagation rules. And in the line sequence setting, we can do something similar by modifying propagation rules, but this only works sometimes. As I was saying before, we can extract countermodels from full derivations in the line sequent and Gentzen sequence setting. Right? The sequence themselves do not have enough structure to define countermodels for the conclusion when proof search fails, but you can extract countermodels from entire sequence in these two settings. And if you define just a regular depth-first proof search algorithm that builds a branch of a proof at a time, trying to find or check if a proof exists at the conclusion, then for the labeled and the tree sequence setting, this will be in exponential space, while it will be in p-space for these two systems. But as I said before, you lose counter-model extraction. Now note that line sequent proofs are technically tree sequent proofs, so you can actually give a p-space algorithm for the tree sequent calculus, and you can also even give a p-space algorithm for the labeled sequent calculus, so long as you don't do proof search in just a depth-first manner on the branches in the proof, but also in a depth-first manner on the graphs that are used in the labeled sequence setting or the branches of the trees. But if you do that, the structure of your sequence are either going to be lines or transitively closed lines in the labeled setting. So you're not really using the full graph or tree-like structure that these two calculi have at their disposal if you write an algorithm in this way. But this would give a p-space algorithm within both of these formalisms, right? But this uses a special technique. Okay, so that concludes the talk on sequent formalisms for modal logics using GL as a case study.